So I don't see there's a few questions in the channel, but I don't know. Oh yeah, Ashley, you're actually here. So cool. We can talk a little bit about things that you raised. Some of these I feel like are more like discussion kinds of things that I'm happy to open for discussion. Um, a lot of these are not things that I have a lot to say about. Oh, the first one, yeah. Okay, so follow up on Russ's talk. I'd be interested in a breakout session where we discuss coding best practices and the 10 simple rules for scientific code review in more detail. So maybe we can do a little bit about that. And particularly maybe this is something I didn't quite get to in either in the Python libraries or in the GitHub tutorial that actually puts both of those together to some extent, which is to talk a little bit about continuous integration. So maybe I'll launch into that and show you a little bit about continuous integration, how to set that up and how to work with continuous integration, because it puts together, I think, some of the things that we talked about this week. And I think of it as like a really good way to implement best practices, in particular, software testing. So I'll kind of catch up everyone on what we're talking about, and then so if you weren't in either of the sessions with me earlier this week, then I'll kind of catch you up quickly on that. So what we did do in the sessions that we had on the Python libraries was to write some Python code that does some simple calculations, simple geometric calculations. We have here this module called circle that contains two functions, one for calculating the area of a circle, one for calculating the circumference of a circle. And during the session about the Python libraries, we organized the code. We started with this code being in a notebook, mixed in with other things like reading data from file and writing out data from file. Maybe it's mixed in with visualizations, kind of like a typical project. And we started by pulling that out into a separate module. You might have noticed an example of this kind of model today in our talk about the data showcase. There was this file utilities that was right there. It's kind of a way to implement this is you have this module, it's alongside your notebooks. And then we increasingly pulled things out into the structure of the Python library. So here we have a Python library. And one of the things that we did along the way was to implement software testing. So I did this a little bit quickly towards the end, and so I'll kind of repeat the idea behind the testing. So the idea behind the testing is to write code that exercises the functionality that you wrote in such a way that it tests it against verified results. These can be verified in various ways. One way, for example, for the calculation of, say, the circumference or the area of the circle, is to take results for which you know the answer, right? So let's say, I mean, you can imagine for more complicated, it gets really complicated for more complicated kinds of analysis methods. But for a lot of analysis methods, you can compute to some level of accuracy or tolerance that a result. So here it's very simple, right? If the radius is 1, then the area is going to be pi, and we know that, and we can verify that. It gets a little bit more complicated if this is like a statistical computation, the kinds of things, say, that Steph was showing in the previous session. You have to think a little bit more about how you do this testing. But in the simplest case, what you will do is you will write functions that assert certain results of the execution of the code. So in this case, we're asserting that the area of a circle with a radius of 1 is pi. And this is the assert statement in Python. This is the structure of the assert statement. It's got the statement here, so it's a statement a little bit like the definition of the function assert. And then there's a Python little piece of Python code. It can be bigger than that has a Boolean. Every piece of code actually has a Boolean of Python code has a Boolean value associated with it. And if it's this kind of logical comparison, then it's one that can take the value false or true, depending on the whether this comparison is true or false. And then after a comma, you can optionally introduce an error message that says when this is wrong. So this is generally the idea of a test. And the particular implementation here follows a very specific set of rules. The rules are this lives in a folder called tests. It's at the top level of our package, and in the tests folder there is a file that starts with tests underscore name of module.py, and inside this file there are functions that start with test underscore name of the function. In fact, it doesn't have to be name of the function. That's a kind of a convention, but it does have to start with test underscore. And the reason that we have to have these test underscore is that we're going to perform automated test discovery. We're going to use a command line tool that performs automated test discovery. If we run it inside of our file system, it goes and searches through the file system for files that start with test underscore something, and inside those files it looks for functions that have the same, they start with test underscore something. And it will run every one of those. So let me go to where we have this code in my hub. Here we are. And the tool that we will use, and now I realize that I need to probably install it, because if I remember correctly, it's not yet installed in the hub yet. It's called PyTest. PyTest is what we call a test runner. There are a few different ones. There's actually one that's built into the Python standard library, but we're not going to use that one here. Instead, we're going to use PyTest. PyTest has some nice features to it, and I'm going to install it, and you can also install it using pip install PyTest. I believe that what happens when I type pip install PyTest here and install it is that it does install it, but if I restart my my hub, then it will be uninstalled, because what we do is we pull down, we create this environment from a Docker image that has very specific things installed into it. So later I will also set that up in the image, so that next week we have that. But if you're following along, you'll need to pip install PyTest, and then as you can see, that happens pretty quickly here. And now if I run PyTest in here, it goes and performs. I do need to also install this library. Okay, so I'm installing our software in here. It's sending some warning about. Oh, interesting. Let's see if that works. If it works. Okay, it does work, I think. So it's discovering the test. So what it does, like I said, it starts a test session up here, and then it goes and it finds every one of those functions, and every function here is going to be like an item.
Just interrupting.
Oh, yes, please.
They said, can you please share your screen?
Oh, God, sorry. Sorry about that. Okay, here I am in the source directory. There's a folder called tests here. We're also in GitHub. Also, let me paste this into. All right. Okay, so I did a bit of installation up here, just repeating this pip install PyTest in order to get this installed. And then also in the source code, I had to go in python-m pip install dot, which installs the software that we wrote. Again, the software, in every session that we run on the hub, we'll have to sort of install it unless we set it up to install this as part of the environment of the hub. So for the purpose of the example. Now, what PyTest does, as I said, is it starts a test session, it reports some things about the platform and the versions of the software that it's running and so on. And then it goes and it collects items. In this case, there are 3 items, because in in here, there are 3 functions. Each one of these functions is counted as an item in this session. And it will go and it will run every one of these items, and it runs these assertions. So if it hits an assertion that's incorrect, like it hit this assertion that's incorrect, we'll fix that in just a second, it'll register a failure. And if it doesn't hit any kind of error or failure during the running of a function, then we'll register a nice little green dot here that says this is fine. Now in this case, it ran into not an error in the calculation, but an error in just the setup, and that's because I did not import calculate up here. So now if I go here, I can test that, and now it passes. Okay, and so this is like a cycle that we'd like to repeat many times. Maybe we add another one here. Let's do a little bit of test-driven development, test, calculate. Let's do something easy here, diameter. Assert, calculate, diam, 1 = 2. I'll do that. Okay, so now I'm doing, note that in my geometry source, geometry circle, there is no calculate diam at all. So here I'm doing what's called test-driven development, in the sense that I'm starting by writing my test. I'm saying, I would like there to be this thing that is called calculate diam, that when I run it, and with input 1, it gives me 2 back, because the diameter is equal to twice the radius. And now if I run my tests, it will necessarily fail because this thing doesn't exist. It's not yet defined. So now that I've verified that the test, I go and I look at this and I say, this is the test that I would like to pass. Now you can think of this like a contract. Now, what do I need to do in order to fulfill this contract? Well, I need to go in here and define def calculate diam r, whoops. Calculate the diameter of a circle, parameters are float, the radius, return float, the diameter. Okay, and then I'll implement that as well. Calculate, return 2 times r. Okay. Now, if I run the test, it still fails, and that because I need to also import that. Yeah, I need to reinstall the software now with this new component. And now it works. Okay, so that's the full cycle, sort of the test-driven development thing. Maybe I do git status, git diff, git branch. Where am I now? Working. I'm on main. Git checkout the diameter. Actually, let me wait with that just a second before I commit all this. I'll do some more things. Okay, so I've done this, and now I want to automate this kind of process a lot more, which is where we started off with continuous integration. So now what I'm going to do is I'm going to go, to the repo, and I'm going to set up continuous integration here. So a few words about continuous integration. The idea behind continuous integration is that it's going to be built into GitHub. I'm going to build into GitHub. I'm going to tell GitHub in a formal way, using sort of a formal language. I'm going to tell GitHub when certain operations happen on this repository, I would like you to execute the following steps, or the following sort of pipeline of steps. And the way that this is implemented is by creating within the directory another directory called .github. Not to be confused with, there is a directory called .git in here. The .git directory is the Git repository. It contains all the information that Git needs in order to track whatever is going on in this repository. The .github folder contains information that's only pertinent to GitHub, the website, not Git, the version control system that is listed. Inside of this, we can put all kinds of things that pertain to GitHub. In particular, we can create another directory called workflows, and then within that, we're going to put some things. In particular, I'm going to find, I have a file. I've done this before, so I have the necessary. I'm going to show you how to do it on GitHub. Let's see if I can make that happen. In the settings, actions, general. I need to remind myself how exactly I implement actions on GitHub. Maybe here. Yes, here. Okay. So we're gonna use their system. So among the tabs that you have at the top here, there's one tab called actions. And if there are actions already implemented on your repo, then here's where you'll see how they ran and stuff like that. If you don't, then it will say, well, do you want to add a package? An action here, and it will give you this kind of suggestions based on what it's seeing, the files it sees in the repository. The one that we want here is we want this Python package. This is what we have here. We want to do something for a Python package. So take this, and what this does, when we click that button, it creates this .github folder with the folder inside of it called workflows, with a file inside of it called Python package.yml. And in here is in this language called, in this markup language called YAML, yet another markup language. I swear that's what it's called. This markup language describes what we would like to happen and when. So it's got a name, and we'll recognize this action by its name. It describes up here in a comment what it does. It installs Python dependencies, it runs tests and links with a variety of Python versions. And then there's a link for how this was created. So it'll do this when we push into the branch main and when we have a pull request against main. This section up here describes when this action is executed. And then down here are sort of the jobs. There's sort of a section up here about where this is going to run. This is going to run on the Ubuntu operating system, the latest. There's some strategy that's set here. I'm not exactly sure what that means, but it also tells us which Python versions this will be run on. And I'm already going to edit this, and that's because we set the software to only work with Python versions 3.10 and above, so it wouldn't work on 3.9. And then there are steps. The actions, the GitHub actions, there's sort of an ecosystem of actions, and some actions use other actions, and it's kind of complicated, but there's an action called checkout, which checks out the code and sets up Python. Sorry, there's one action that checks out, and then there's another one that sets up Python. Here it is with a specific Python version. Notice that we have different Python versions, so it'll do it twice, once with each Python version. And this is the syntax that is used in order to kind of fill in this kind of template with some variable, and then it'll run the following. First it'll install or upgrade the installation of pip. Then it will install flake8 and PyTest. I'll explain what flake8 is in just a second. And then it checks if there's a requirement.txt, then it'll install the requirements from there. I'm going to delete this because we don't have requirements.txt. Instead, we have everything configured in our Py project file for this. So I'm going to delete this line. Instead, I'm going to let it run these things. And then I'm going to add one more step here, which is install a package, which will use python-m pip install dot, which is what we do in order to install the package. So this along the way will also install all the software dependencies of our package, I believe. And then it's going to do two things for us. The first is it's going to lint the software. I'll explain that in just a second. But finally, you'll see here it runs PyTest. So it runs automated test discovery and reports back to us exactly what we did. It'll run exactly what we ran up here with these tests, right? So that's going to be part of the point here, is that it runs this on GitHub for us after having installed all the dependencies, set everything up from scratch from our code. The linting, just a note on that. Flake8 is a little command line tool that checks that the code is not flaky and that it complies with what's called PEP8. PEP8, again, another best practice in writing Python code is to write code that complies with PEP8 Python, with the Python language style guide. So this one starts by announcing that a foolish consistency is the hobgoblin of little minds, but then, points out that readability counts and then describes all kinds of rules about how to lay out the code, things like how long the lines should be, how many spaces you should use per indentation, things like, there should be 2 lines before the definition of 2 lines of white space before a function definition, and so on and so forth. And so this is all very nice and is a list of instructions, and people have codified these instructions into software in this tool called Flake8. So it checks for PEP8 and then checks for flakiness. Flakiness is a little bit like, is there a variable that's defined but never used in any way? Or are you importing some function or some package that you never use in your code? But those are kind of signs of flakiness. So it's going to check for that, and it's going to check for PEP8, and then it's going to raise an error if the code is flaky in any way. So okay, so we've sort of written out this. We took what they gave us and we edited a little bit to adapt it to what we're doing. And next, I believe we can commit this into the repository. I'm going to write a more informative message here. Implement GitHub actions. And then I'm going to commit this directly to the main branch. Yes, I'll do that. What's the worst that can happen? Usually committing directly to the main branch is not a great idea. Well, actually, let's see what happens and now I'm curious what happens if I create a new branch for this and start a pull request. So I'm going to do that, and GitHub knows how to take this commit that I just made and make it into a pull request. And I'm going to create the pull request. So here we go. And it gives it some name, Rokem patch1, that's the name of the branch. And then it checks for, and it says there are no, and here it's starting to do stuff already. So because this pull request implements actions on the repository, it's already running stuff. So here we can go and see what's going on. If you go and click on this thing, it's showing us, here it's installing, it's running python-m pip install dot, which installed the software. And then it had some error on the linting. So that's good, I guess, in some sense. So it caught some error here along the way, and that's actually good that it failed with the linting because it noticed that I'm using a name in the test. Actually, it noticed that I'm using a name calculated circ that is undefined within that context. This was in this code. I wrote code for the test, but I forgot to import. You remember at the start now, I did this additional import. So it didn't have that. So that's why it's pointing out this is flaky and has this big red cross here and doesn't like that I did that. So now I need to fix that. But instead of fixing that in here, I'm going to merge this code here with its error, and then I'm going to fix it on a subsequent pull request instead. Oh, should I do that? Maybe I can make this green here. I'm trying to think what would be less confusing. I think less confusing to go ahead and merge that and then work with that. And this will also show you some kind of like a bit of Git kind of workflow with these kinds of situations. So I'm merging that in, even though it's got a big red X here, because I'll need that in order to fix it. Usually you don't want to merge it when it's like that, but in this case, we're going to go ahead and fix it. So now what I'm going to do is I'm going to remove the directories that I created locally because I created them on I created those on GitHub and I don't want conflicts with render. Okay. Status. So right, I have this additional stuff that I haven't staged for commit yet. I'm going to check out git branch diameter, because I've implemented calculation of diameter in the code that I did before, and then git checkout diameter, git diff. I still have these diffs of like the stuff that I just added. Git I'm on branch diameter, right? Okay. Git commit, git add source geometry circle, git add test circle, git commit dash n adds implementation of diameter calculation. Okay, git push origin diameter. Right, great. And I'm going to already go ahead and create a pull request with this thing, which is this new addition. Great. So that's checking for the ability to merge automatically, which is possible, but I'm not going to merge that yet. Instead, what I'm going to do is I've created this, but remember I made some changes on the main branch by adding this additional configuration file and so on. So what I'd like to do here now is, before I move ahead, I'd like to go to main, git checkout main, and git pull upstream main, which pulls down here my Python package YAML configuration file and this, well, some changes that happened to the README. Basically, I fast forwarded to where the main branch is right now. So I have two branches right now. I have this diameter branch, I have this main branch, and I've updated main branch. And now what I'm going to try to do is update the diameter branch so that it has all the up-to-date changes on the main branch as well. So I'm going to check out diameter, and I'm going to git merge main into here. So that this is the strategy that I'm going to take in order to update this branch so that it's as close to up to date with the current state of main, is to try to merge the main branch in here. And it's trying to do that. Oh, it opened some funky editor here. But merge made, so that seems to have worked fine. So now I'm going to push diameter, origin diameter. So just for kind of like, for a little bit of context, there is this merge of the pull request that implemented the GitHub Actions. Then there's the addition of the implementation of the diameter calculation. Then there's another merge, which is this merge that I just did, adding, so our diameter branch has in fact everything that is in main, and also this additional implementation of the diameter calculation. So now, if we go and we git push origin diameter, then it will update the diameter branch with this merge. And because this includes the configuration, it now also tests. Whoops, I stepped on that cable and now I can't see anything. Sorry about that. Okay, so now, because this includes this configuration for the actions, it's going to run the actions. And now notice that oh, sorry about that. Oh, now you can see me. And I'm going to share my screen again. Right. So now all checks have passed. And that's because along the way, we fixed that issue with, you remember the flake 8 issue that existed, that it didn't have this calculate circ? That was actually fixed on the branch. It was fixed right here before we added diameter. So it was included in the things that we pushed together with this diameter calculation. So now everything is good. If we go to details, we'll see, it actually shows us what this view shows us is a view into the machine on, in this case, the Azure cloud computing service, where it's kind of like setting up the job. It's running this checkout operation. It's setting up Python 3.10 in this case, installing the dependencies. So it's showing you sort of the things that are in the terminal when it's running this thing. It's running the installation of the package, also looks similar to things we saw in our own terminal. This linting, we haven't actually done the linting. Well, that's interesting. It's got some issues here, but I think that it's ignoring some of these things. Maybe. It's got some issues, definitely, here, but we'll I think it's intentionally ignoring these things like trailing white space and things not being used inside the context of a dunder init file and so on. And then it's testing with PyTest. So you can see it ran the full kind of testing operation here. And then it's doing some post job cleaning and gets out of there. And because each one of these steps worked, then the whole thing is green. And here it does the same thing, but with a different version of Python. And you can set up many of these to work in parallel by in this file that we have here, by setting up like other kind of matrix. You can have many different versions of Python, many versions of other dependencies. So now we have oh, now it's saying this is red. Oh, it failed here. That's interesting. It worked on the branch, but didn't work here. Okay, it's not liking something that I did. Oh, I didn't merge the thing yet. So now, okay, so it's green here. In the pull request, it's green. On main, it's red because I pushed it in even though it was red on the previous. So now we see that it's green. The benefit of this in terms of code review is that now I can go as a reviewer, if you're somebody else reviewing this code, not me as a contributor, but somebody else as a reviewer, you can go and see, okay, this makes sense. This test makes sense. There's this additional test that also makes sense. Everything looks okay. Now, if everything in terms of the testing, the implementation looks like it's fine, that's still not a guarantee that this will work. In general, not a guarantee that this will work on any machine, right? Just because it worked on the machine on which this person was working that pushed this code, you want to know that it would work on any kind of generic machine. That's the purpose of these actions. It's running on just kind of like a blank machine that has nothing on it, following a very clear set of steps. And more than that, also, as a reviewer of the code, I might be disinclined to download this, install this on my machine, run the tests manually. That's a lot of work that I don't want to do. Instead, I want to look here and see that everything's fine. So it's testing for me that the code is properly formatted, that the tests are passing, everything is good. I can look at the code, focus on whether the content makes sense. And then I know, because this ran, I know that this will work on just a generic machine. So if everything about the code looks fine to me, I don't need to download it and test it on my own machine. I can hit the merge pull request button, and that then goes into main. And now if we go to this actions tab, you'll see what we usually see here, which is a list of the runs. What we can see is there was some runs that happened when I implemented that, and then when I opened the pull request, and then when I merged the pull request, and then when I opened another pull request, and then when I pushed another commit into there, and then now this is the merge into main. And that's because the configuration file says, please run this when I make a pull request against main or when I push to main. And this is considered a push to main. So now main is also green. If I go here, I see a little green check mark here that tells me that GitHub Actions ran and it all works. Okay, let me pause there for a second. What questions do folks have? Yeah.
So I have a question about the tests conceptually. If you have like code that is running some like more complicated analysis, like very density specific to your project.
Yeah.
And not like building a library for like, the people to use.
Oh, yeah.
What is the use case for the test, and like how do you conceptualize the testing? Or should you even test it? If you think yes, like how do you conceptualize? Like I guess I just can't think of like a simple test to make sure it works without using my data.
Right. So part of the challenge for us as people who do data analysis, that if you want to implement tests for a particular data analysis, then you need data.
Yeah.
Right. And that makes it really tricky to write tests in the context of like some data-free thing.
Yeah. So
I'm hesitant, but I'll show an example of a really complicated library that I work on, DyPy. Here is DyPy that implements actions. So here's our actions. And then what I'm going to try to show you here is just a little bit of the complexity here. So this is the list of all the workflows that run when we do various things. So there's many different kinds. There's something code spell that checks spelling, actually, just spelling in the English language. So the documentation is in good shape. But here, for example, we're testing with optional dependencies. The software has some dependencies that are optional. And then I'm going to show running the tests. In this case, running the tests is a 36-minute operation. And along the way, it's testing hundreds of things. And one of the things you see it doing here is it's actually downloading test data from some place. We put it on Figshare and running through all the algorithms in the library. So here the solution is to download some example data from somewhere. And you have to be a little bit careful because these machines have limited RAM. You usually have limited time. I think we're limited to like an hour. We can't go more than an hour here. So you have to kind of be economical about this. And then you run all kinds of analysis. We're running all kinds of analysis. I mean, another context in which you want to do these kinds of things, like running on data, is in the context where you have a software library, but you have some example that requires also some data. So I guess another example, I showed a little bit of AFQing earlier today, is this library PyFQ, where we have an action that builds the documentation. Like we have some, I don't know, getting started, I guess here, there's, in the beginning, there's something that downloads some data and organizes it in bids, in some bids way. So, and then later on, you kind of see, here's the data. So it runs the data analysis. And so you can build these kind of automated documentation also, that the GitHub Actions runs the documentation. I'm coming back to this here. Here I implemented a very kind of very general Python kind of workflow, but you can imagine instead of running, you can run any kind of command here. And so you can apply this idea of the GitHub Actions of this continuous integration to many different things. I'll show you an example, a recent example from my group that I'm kind of proud of. Oh, I need to authenticate like this. Let's hope that works. Is a poster that we wrote for OHBM, and the poster gets built on GitHub Actions using it's this R library, and then it kind of gets pushed to like a website, so you can see our poster on this website here. Oops. And so the nice thing about this is like if I work together with some co-authors and we're kind of tweaking this thing, we can, through pull requests, we can kind of like add things to this poster and incrementally change the poster and get it automatically built, always in a consistent way. We don't need to sit there and like run this particular R software and make sure that we all have the same fonts and all this stuff that you have to deal with when you're trying to do this kind of thing on multiple different machines. Or in my opinion, worse yet, like send back and forth like a PDF file and like have like the versioning hell of like, I worked on this time on Tuesday, I worked on this file and I'm sending it back to you. And we're doing, so you can use everything that is kind of like the nice thing about getting GitHub there. You're simultaneously working on the same thing on different branches. You can do that here as well. So this is just an example of like a pretty unusual, but fairly useful use of continuous integration. Did that answer your question? And maybe some other questions you didn't ask, probably. Okay. Let me go back here. What other questions do folks have about this kind of continuous integration? So I've done this now for posters. The course that I taught in the spring is all on GitHub, and the slides are all like built through continuous integration using something called Quarto, which is a very nice library. Also, it's kind of in the R world more than Python. The Quarto is a way to sort of build slides out of markdown files. I used all that. Written grants this way, where the PDF just gets built using LaTeX every time. Okay, enough about continuous integration. What else can I interest you in? Let's see what's. Okay, should I continue with Ashley's? Okay, so there's a question here that's I think a little bit more of like in the socio-technical realm. We talked about collaboration patterns, and Ashley in particular wanted to get involved in open source projects in the neuroimaging Python ecosystem, but find the idea intimidating. And so we can have a little bit of conversation. I can give you my 2 cents, and then maybe others can also pitch in about contributing to open source projects. So this one's a little bit about more about the social process, like how do I go introduce myself? I think first as a tip is to go about the process by scratching your own itch in a sense, right? It's like if you're a user of a particular project, then it makes sense for you to become a contributor. You know this project already, you know what it can do, what it can't do. Maybe you have some ideas about how to extend it. Maybe you start by sort of pointing out things that are not clear in the documentation, or people really appreciate those kinds of comments. Actually, I think Noah said this earlier today as well. When I develop some tool and I'm really deep, I'm kind of close up to this thing and I kind of understand what it does pretty well because I wrote it. It's hard for me to anticipate what some potential user, and for a lot of these open source software projects, if it has this kind of documentation and intention of being used by many people, the hope is that it won't be hard for somebody who doesn't know the software well to start contributing. So a really good place to start contributing is in documentation on software that you already use. So if you're using some software and you point out, even maybe make pull requests with fixes to the documentation, that's often very, very welcome. In general, it's worth looking at the history of the project a little bit before you propose changes to see whether those changes were previously proposed and rejected. I don't know if you're like, one example I can think about is you go to some documentation of something and you change all the American style spelling to British style spelling on all the words that can be spelled different in those two spellings, and you propose that as a change, that might be unwelcome, because maybe that's something that people decided on long ago. We're going to go with this spelling, not with that spelling. So it's not a bad idea to go to a project that you work on and post an issue and say, hey, I'm really interested in this project. I'm looking to contribute. Are there any issues here that are really easy for new contributors? Often GitHub repositories will have, let me see if we do this on DiPy. Maybe we do this on DiPy. Yeah. So I'll go back to DiPy. If you go to the issues page, which is where people post sort of bugs and requests, there's like a beginner friendly tag, right? So these are all the issues that are beginner friendly. So this is a good, so often projects will tag issues with different kinds of tags, like what is this, a bug fix? Is it in what category? Is it documentation? So for example, this one on how to load and save clustering results. Let's say that you're using the clustering tools in DiPy already in your work and you're new to contributing to this. Going in here and saying, hey, I'm really interested in this. I've used this and I think I know how to do this. Can I take a shot at this? And then the maintainers of the project will obviously, this has been around for a while now. Yeah, more than a year. So obviously nobody else has picked this up. So that would be really welcome. And then you can go ahead and start with that and then kind of see where you get, try to interact with the project through kind of the issues. So that's an approach to that. Does anybody else have experiences to share about this? Maybe anyone on Zoom who's contributed to open source and how that happened for you? Okay. I've answered a few of Ashley's questions and wanted to give a chance in case there's anybody else who has some topic that you're still kind of interested in either hearing more about, discussing, questions that remain from things we talked about throughout the week. I will continue here with Ashley's list then. So the next one is about prompting for programming, and I don't know much about that. I mean, I use Copilot in VS Code, but I don't have a ton of experience. I've found that, so I'll just show one thing about Copilot in VS Code that I find to be kind of fun, which is that in addition to the fact that you can now let's do a little bit. Why not? Let's put that somewhere. Okay, that's reasonable. That's pretty reasonable too. Go on. Okay, fine. Not the cleverest code I've ever seen. But so in addition to doing this kind of prompting, one other thing you can do is there's like a chat mode in here. And you can ask questions. You can say like, oh, in this code, I actually wanted something that would return a view into just one time point in a time series. And then it'll propose some update here. And I can actually, I think I can click on this and it will replace that code with the codes that are being proposed here. So you can chat with Copilot here in this little chat thing and ask it to fix things for you. Could you please add a doc string? Okay, here's a doc string. Make the doc string compliant with the NumPy doc string standard. Not bad. Okay. Fine. Not Pepe compliant, by the way. This ruler here on the right is the length of the line, and maybe I'll ask it to be Pepe compliant. Let's see if it manages that. No. Okay, that's just this line is too long according to Pepe. Whatever. So here you can have kind of like iteratively work with Copilot. So that's the only real tip I have. Let's see. Any other tips on prompting LLMs for coding? I think there's like a lot of work being done on that right now. I know Anshul and others at the Software Engineering Center have been doing a lot of work on kind of like teaching people how to do this. And there are like much more systematic ways of doing this that I don't know much about, except to say that they exist out there. Anyone else have thoughts? Okay, I will take this other question now and take a break with from Ashley's. I can come back to that. But questions for learning math that's online courses for learning math that's necessary for ML that you would recommend, or topics for that are relevant for ML. So I think the two kinds of things that I would recommend is like a basis for learning machine learning. I had some conversations after the machine learning tutorial about resources. So I might have posted actually links to, but if I haven't, then I will post links to like really great books to get you started. Yes, here, these two are really great. One of the things so this one is a little bit, Stat Learning is a little bit more gentle in terms of kind of the mathematical basis that it expects. This one's a little bit heavier. Generally, both of these assume that you know at least some linear algebra and some probability. And both of those things are I think kind of like foundation for learning about machine learning methods. If you want more than that, learning a little bit about optimization methods, numerical optimization methods is quite useful as well, because many machine learning methods use optimization. If you want to understand like why they're failing and in what ways they're failing, knowing a little bit more about the implementation of these optimization methods can be helpful. So that's kind of a little bit more. Yeah.
There is a winner off of an intro winner health workforce that was on Dummy. That was like $20. That was really helpful as like a precursor to machine learning stuff.
This is on some platform.
Yeah, it's called Udemy. It's like a Coursera.
Oh, Udemy. Okay.
Yeah.
So I'll maybe we'll put that here.
Yeah.
Do you think you can drop that into
Yeah.
the Slack? yeah, maybe, so the recommendation here is for a Udemy linear algebra course. If I caught that correctly. Oh. There, cool. What else over here? Python, neuroimaging Python tools and neuroimaging standards. So I think just out of curiosity, and like I'll do this for the room, but also for Zoom. Just maybe raise your hand if you are if you're familiar with Nebabble. Nebabble? Nibabble? Nebabble? Okay, well, maybe let me say a few words about Nebabble, because it's kind of like the foundation tool for anything else that you might do with neuroimaging in Python. And so it's a very useful tool. It's the most boring tool you can imagine, because what it does is it takes data stored in neuroimaging file formats and it returns to you, it gives you that data in NumPy arrays. And that's all it does pretty much. It does very little except for that. But that is like step one in anything you want to do. I mean, that was this code right here. So this code demonstrates how Nebabble works quite nicely. Thank you, Copilot. You give it a file name. Let's say it's a nifty file, like an nii.gz or an nii, and it reads that file here. And then interestingly, and kind of importantly for Nebabble, is the fact that it does this two-step process here. So I'll kind of explain why there are two lines of code here, why image is not already the array that you were interested in. There are a couple of reasons for that. The first is that sometimes when you're working with neuroimaging files, you don't actually want to read all of the data into the memory of the machine. Maybe it's a huge array of data with 4 gigs of data, something like these diffusion data from the Human Connectome project that we talked about earlier. And so you don't want to do that. You want to know, for example, what shape this data has, or like something about the spatial transformation between the scanner and the data array, or some other kind of property of the data, but not necessarily like every single number in there. So what this allows you then to do is to load, it lazy loads the file. It says, this is where the data is, and image now, when you read it, image is an object that contains header information. Maybe I'll demonstrate this instead of here, I'll demonstrate this here. Let me get wrong plus, this is the plus I wanted. Import Nebabble as nib.load, and I think there must be inside of home, Jovian, shared. I think there must be some data in here. Oh, this is all EEG data. Joke's on me. It's funny, we don't have a single Nifty file here, huh? Let me get some Nifty. I know where I have some data. Let me grab some data from my local machine. Okay, here's a T1 weighted from some example data. There it is. Okay, good. Nib.load sub-1, session 1. So this is a T1 weighted data. Or I actually could have used the cloud paths that I showed you before. That would have worked too. But let's show it in the simple case here. This happened very quickly, and that's because image, this thing is what we call a Nifty 1 image. It's a kind of object that doesn't have any data attached to it yet, but it does know, for example, it knows the shape of the data. it knows that the array of data that's stored in this file is 81 by 106 by 76. And if you want the data, it can give you that data, get F data, and that F is for floating point data. So this, if the data is not stored as floating point, it will convert it into floating point data for you. So it always comes in kind of some predictable way. And now, the type of this thing is in fact an NumPy. So MeBabel is really useful in that respect. Now, this thing will also have, and this is something I feel like we don't necessarily teach this thing a lot, but it's kind of important, is that it comes associated to a spatial transformation, like something about where the subject's head was, or where this volume that was used to acquire this T1 weighted data is relative to the isocenter of the scanner. So this tells us that the corner of this volume is someplace in millimeters relative to where the isocenter of the scanner is. And this is important if you're trying to put together different data that was collected from the same subject in the same session, for example, anatomical and fMRI data. You need to be able to resample the data from one kind of volume to another, or from one coordinate frame to another coordinate frame. Because often when we collect T1 weighted data, we collect it at very high resolution with a particular field of view. We collect bold, we collect it maybe with a lower resolution, with maybe a smaller field of view. And those, if we just put those volumes together, the brain would be in different places in these two volumes. And so one way to deal with that is to describe how you would go from a coordinate in the array, like I am now in position, I'm in data 0, 0, 0 or 0, 0, 1, where is that position, the position 0, 0, 1 in the spatial coordinate frame in millimeters of the scanner relative to the isocenter of the scanner. And that's described by this 4x4 array. Now, how is this described by the 4x4 array? Requires a little bit of linear algebra, so I'll just talk about it for a second here. There's a few, the way to think about it is that matrices describe transforms in space. Let me show you a picture. We wrote about this a little bit in this book that I wrote, so I'm going to show you this here, maybe. Yeah, so here's an example of a bold array and T1 weighted. It's from the same subject, collected in the same session, so we'll assume that the head is in the exact same location. But the problem is if we take the data from the last dimension in the T1, in the middle of the last dimension of the T1, and we get this kind of sagittal with the person looking up. If we take on the bold, the middle of the last dimension, we get this kind of horizontal slice in the middle of the head with the person looking rightward. And so we can't put those data together like this. Instead, what we're going to do is we're going to look at this, what we call this 4x4, by the way we call it the affine of the file. Out of curiosity, who here has kind of heard about affines, used affines? Is this like completely redundant? Sort of. Okay, good. This is stuff we should be teaching anyone who touches neuroimaging data before they touch neuroimaging data. And I feel like I had to sort of learn it a decade into working with neuroimaging data. I had to learn it systematically. So the affine is this 4x4 matrix. One way to think about these matrices is that they encode transformation. So if we have a coordinate, an XY coordinate, for example, in the plane, here it is, an XY coordinate right here. And we multiply it with this matrix. So this requires a little bit of an understanding of linear algebra. If we take this coordinate here and we multiply it with this kind of matrix, this is called a rotation matrix, and this is a rotation matrix in 2D. What happens to the XY coordinate is that the entire vector described by this is rotated by an angle theta on the plane. And the same can be done by, you can also scale let's say that we hit it with this 2x2 matrix instead, AB, that would scale this vector, the distance. Let's say that that we had a coordinate, XY coordinate 1, 1, this would move that coordinate to the location AB instead. If it was 1, 1, it would move it. So if we had the coordinate 1, 1, and A and B were equal to 2, now it would move 1, 1 to 2, 2. So that's what a matrix does to a coordinate in space. And so now we have a scaling matrix over here. We have a rotation matrix over there. If it's a three-dimensional coordinate, which is usually the case for neuroimaging data, you can apply the same idea, scaling by multiplying it with this matrix, which is a scaling matrix, or multiplying it with these three matrices, which are rotations on the kind of x-axis, the y-axis, and the z-axis. So we can decompose the rotation into rotations along each one of the three spatial axes. And we can compose those together if we take and we multiply this matrix by that matrix, and then we multiply the product of these two matrices by some coordinate. We're applying simultaneously a scaling and a rotation. Now, one thing that a matrix of this dimensionality can't do is a translation. And for that, we need to create what's called an augmented matrix. So for a three-dimensional coordinate, an x, y, z position in space, we can multiply it by this kind of matrix. Here, A total includes all the scaling and the rotation that we want to do. So, for example, the rotation between these two kinds of things, right? We kind of have to flip things around and rotate a little bit and so on. So that's the rotation matrix, is this A total in here. And then that also includes the scaling, both the scaling and the rotation go into A total. And then here on the fourth column, we put the translation. There might be some translation between these two images as well. We put the translation here, and then we put a row of zeros and a 1 here. And then we take the coordinate that we're interested in shifting, and we add a 1 to its end. And then we take this 4-dimensional coordinate that has 1 in its last dimension, and we apply this 4x4 matrix to it, and that applies both a rotation, scaling, and translation to a coordinate. So now we're able to do all if there are two images and one is like rotated and shifted and scaled relative to the other because their resolution of the voxels is different, we can do all of these things with this kind of 4x4 matrix. So that's it's called an affine because generally a 4x4 matrix can apply any affine transformation. A 3x3 matrix can apply a linear transformation. It's called a linear transformation. So that allows us to do scaling. It allows us to do rotation, but that's it. And then a 4x4 matrix allows us to do scaling and rotation and translation, but also weird things like shearing and I think that's it, and shearing. So, which we don't want to do here because we think that shearing is like changing the shape of the thing, and we don't think these shapes change. So we're only going to do some of the things that we can do with 4x4 matrices, which is all these scaling, translation, scaling, rotation, translation. That's it. Okay, in practice, this is done by looking at these affine matrices that come along with the with this data. These affine matrices describe how you take a coordinate. For example, I'm sitting in coordinate, let's say I'm sitting in the origin, right? 0, 0, 0, 1 of one of my images. The question is, where is this in millimeters in the scanner? And that's answered by taking the affine and multiplying. This is matrix multiplication in Python, multiplying that by this origin. So this tells us where in space is, how many millimeters. I think this is like left, up, and forward we need to go in order to get to find where this voxel is in space. And we have that both for the T1 and for the bold. And so in order to go from one to the other, let's say we wanted to know where 0, 0, 0 of the T1 is in the space of which coordinate should we go to find the location in the brain that is in 0, 0, 0 in T1, where should we go? What coordinate should we go into the bold? And so what we do there is we go into real space, we apply the affine to this coordinate 0, 0, 0. We go into real millimeter space, and then we take the affine of the other image we're interested in, and we take the inverse of that affine. So matrices have inverses that apply the same operation, but in the other direction. And we apply the inverse of that matrix to the location in the space. And that takes us back into the coordinate frame of this other image. So the operation in full is, if we want to go back and forth, is we apply one affine to the coordinate, and then we apply the inverse of the other affine. And we can actually compose those together as well. So we can compose transformation from one space to the other by here is the inverse thing. This explains how to compute inverses. By taking, so here we're taking the voxel in the center of the bold, and we apply the affine of the bold to that, and that puts us in the scanner coordinates in millimeters, and it's got some negative numbers, and that's because this is relative to the isocenter. So you can be like to the left of the isocenter or to the right of the isocenter, and one would be negative and the other would be positive. And then we take the inverse of the affine of the T1, and we take the bold, the center of the bold image and the scanner coordinates in millimeters, apply this kind of inverse affine, and that brings us back into the T1 coordinates and tells us something. This is approximate, right? Because it's got like these decimal points, but roughly in 147, 133, and 88 or so is where we want to be, right here. And fortunately, Babel makes this a little easier than that, because it lets us apply this resample from to function. So in nebabel.processing, there's a resample from to, and this kind of like the real take home here is you have two nifty images, and you think they're well registered to each other, but they're not they're not aligned to each other. So they're registered in the sense that the brain, if we put them back in the scanner, the brain would be in the same place, but they're not aligned to each other in the sense that coordinate 0, 0, 0 doesn't refer to the same place in the brain. You can take one, for example, the T1 weighted image, and you can resample from the T1 image using the shape of the XYZ, the three first dimensions of the bold image. And here we're using just the three first dimensions because those are the spatial dimensions, and the fourth dimension is the time. And the affine of the bold, and you get here the T1 data resampled already to the space of the bold data, and we can kind of show that by now looking at the result of that, same as before. Now these things look like they're from the same place in the brain. So that's kind of, and this kind of set of operations here is one that we do, of course, all the time in various guises for all kinds of, a lot of the stuff that Dora talked about this morning as being like really hard for them, and I believe is really hard, is related exactly to this. The electrode is like, we know where it is in the CT scan because that's where we can see it, and then we have to put that CT scan and register with some anatomical image, and then we have to take that from that anatomical image into like the diffusion MRI image, which was collected in a separate session in a different resolution, different field of view, maybe different orientation altogether. And all of those things can be kind of connected together through series of affine transformations between all of these things. Okay, what questions do you have about that? I mean, this is a bit quick, and it is Friday after a long week, so this kind of like pretty heavy. But there, maybe I'll just post this also. So if you want to come and revisit this, this really, I really feel like this is, maybe I'm just carrying a grudge against all my mentors who assume that I just understand this intuitively, that this is the kind of stuff when you first start working with neuroimaging data, somebody should show you this and say, this is how these two images are related to each other. And this continues to be, and a lot of the things that I do continues to be fiendishly hard, keeping track of these things, keeping track of when exactly to resample. And like here, I resampled from the T1 to the bolds, but you might consider, is that actually the thing we want to do here? And consider like when we want to do that in the processing pipeline, what are the costs of doing that? What is the cost of resampling from here, from the original to this, by the way? And just off the bat, a guess, what did we pay here? What did we lose when we did that? Immediately?
Resolution?
Yes, resolution. Yeah, the bold is like a much lower resolution image than the T1 weighted. This one was collected at like approximately 1 millimeter isotropic. This one is, I think, approximately 3 millimeter isotropic. So immediately lost a ton of resolution here. So if we want to do any analysis on the T1 weighted, we want to be careful not to do that analysis on this resampled image. Rather, want to do it in the native and as high as possible resolution, or in some reasonably high resolution, and then take the results of that analysis and apply this transformation to those results into the bold. Okay? So that's something to think about also when to do. All right. Cool. So that was a pretty deep dive into, what was the question? Neuroimaging tools in Python. There are a lot of other things. There's a whole kind of ecosystem. And I think, Ashley, you intended to ask about tools that are more kind of specific. So one thing that I'll mention here that's kind of a cool set of tools is NePreps. So the NePreps are the neuroimaging pre-processing tools, and there are a bunch of different projects. The most, I think, well-known is fMRI Prep, which is a pipeline. It's a BIDS app. It takes BIDS data that contains bold fMRI data and processes it through a very robust and pretty well-validated set of steps in a very standardized manner. And if it runs into issues, it falls back in all kinds of resilient ways on like alternative solutions. And it's been used by one of the advantages of this solves the problem that every lab had their own sort of pipeline that was made out of like best in class kind of tools to do different things, but everyone was doing something slightly different. And what this does is kind of like centralize those series of steps that we all eventually want to do in kind of a centralized manner into one tool. And so now it's been run by a lot of people, which also provides a lot of debugging in some sense, right? Like all the possible failure modes of these pre-processing tools have been ironed out. I should say, for my purpose, kind of like a BIDS app that composes together all kinds of other software tools and pipelines from other software kits mostly, but also includes implementations of certain steps. And so while developing fMRI Prep, Oscar Esteban mostly, who was kind of the person leading the charge on this, realized that a lot of the principles underlying fMRI Prep could be translated to other things like, so now this is a series of different kind of composable tools. There's something called NeWorkflows, which includes common workflows for MRI data. So there are kinds of operations, there are kinds of operations like resampling and transformations between spaces and things of that sort that we do across different kind of MRI data. And so what NeWorkflows collects together are these kind of workflows. They're all implemented using software framework called NePipe, which is a Python library that provides interfaces to other software, things like FSL and SPN and FreeSurfer and a variety of other things. So instead of chaining together those things in long and hideous bash scripts, what NePipe offers is instead to write Python code that provides object-oriented interfaces to all these tools in a uniform way, keeps track of provenance of different outputs, and allows you to execute these things on various computational platforms in a way that you can track what has happened and a way that's efficient and so on. So NeWorkflows takes that a little step further and implements like standard workflows that you might want to use across different kinds of things. And then fMRI prep, for example, uses some of these things for new workflows, but SMRI prep, which is pre-processing of structural MRI, also uses these same tools. So it's kind of like a whole ecosystem here that is built around this, and multiple kind of specific use cases like knee rodents for rodent data, knee babies up here, which is fMRI prep, but for infant data. Infants have very strange brains relative to a human. So it does. And then there's kind of specific things like this thing that I've worked on a little bit, which is like specific things about head motion and eddy current correction and diffusion. And visualization tools as well. There's a whole philosophy here around creating, if you've run fMRI prep, you've seen it creates these reports that you can open and look at. Philosophy is kind of like a glass brain approach, or glass box, not a black box, a glass box that you can look into and see all the steps, what happened to your data in every step. So it creates these reports. So there's knee reports somewhere here. There's knee reports that generates those, and is used across all of these. So hopefully that gave you at least a taste of kind of this question here. Okay, let's see. What other questions do you all have at this point? All right. Maybe I'll say just one more thing about, so we're this the last few minutes I get with you before you all go to your weekend and I go off to my weekend and so on. But about next week is the week next week, we'll start with these hackathon pitches. And I just want to make sure that if you have questions about how that will work and what will happen next week, that we can answer those. I'll just describe what will happen on Monday. On Monday morning, we'll have a session about like collaboration and project management on GitHub. So you'll learn a little bit more about GitHub and how to use it to manage collaborative projects and kind of work together, and that'll hopefully set the stage for the hackathon. So, and then after that, we will do a hackathon pitch session. So in that session, folks will come up, like we're doing it either here or out there. Anyway, they'll come up, you'll say, I want to work on, or if you have some idea, you'll come up and you'll say, I want to work on X, Y, and Z. And it doesn't have to be very fully fleshed out. You don't necessarily, it's good if you know like what data you'll work on or what software you'll use, but it doesn't have to be very fully fleshed out. And then you just tell people in a couple of minutes, maybe a minute or two, just kind of like, what's your idea? And we'll have several of those, hopefully more than two, let's say. And after that, we'll write that in this document that I shared earlier today. We'll write that people can kind of say who's interested in what, and then we'll find each other. Some people may be in person in this room, and some other people might be in person in some room somewhere else and can connect via Zoom. And we have these owls that you can use in order to form hybrid teams or in-person teams or Zoom teams. If it's more convenient, if you're in some time zone where it's very late right now, it might be more convenient for you to team up with people in close to your time zone. But kind of connect with other people over the next minutes, and then off you go, right? Start putting together a GitHub repo for your project and finding the data, talking to us about the software you need, the infrastructure you need, identifying data sets, software, and so on. Any questions about Monday? Cool. Have a great weekend. Be safe out there, and I'll see you on Monday at 9.